We'll now make an observation that you might have already made for yourself, namely, before we discuss the standard inner product on Kn, actually this type of multiplication of vectors already occurred in this lecture, namely when we multiplied matrices. What we're doing when we multiply matrices is that kind of entry-wise we always multiply a row and a column of two different matrices, of course. But if you take a look at the formula, if we view these rows and columns simply as vectors in Km or Kn or whatever, this product of the two is simply the standard inner product of these two as vectors. So this really occurs there. This is an important observation, and this will help us in finding a different characterization of orthogonal matrices. So let me just write this down in detail and then to kind of make precise what I'm meaning when I'm saying this. So let L, M, N be in N, and now we take two matrices of arbitrary dimensions which we multiply. A is, no, I don't need the entries. A is an L by M matrix, and B an M by N matrix in the same field K, and K is R or C. So in both cases this works. Then, when we want to compute the product A times B, so this matrix product, this means we take the rows of A and multiply them with the columns of B. So this has ML different rows. Let R1 to RL be the rows of A seen as, and now this of course is a row vector, so in fact a row vector is a 1 by M matrix in this setting, but here we see them as elements of Km, as we always did. So with rows and columns I was pretty sloppy, so to get the good computations. Now we similarly take the columns of B, so these are now C1 to Cn, be the columns of B, and they are now column vectors, so M by 1 matrices. And again, we want to see them as elements of K to the N. Then, with respect to the standard inner product, on Km, we get the following: the product A times B. So in the first entry in the top left, we take the first row of A and the first column of B, and what we're really doing there, just by definition, is taking the standard inner product of the two vectors. So this would be R1, C1. Okay, here, second entry, first row, we take the first row of A and take the second column of B, so this would be R1, C2, and so on, until we arrive at R1, Cn. Let me just, N, right. So in the second row, we do everything in the same way, but just with the second row of A instead of the first row of A. So this is R2, C1 inner product, R2, C2 inner product, R2, Cn inner product, and so on and so on. So in the final row, we have RL, C1, RL, C2, RL, Cn. This is actually a useful way of memorizing the matrix product in case you can memorize. So you don't need to learn matrix product and inner product, because if you've understood one, you've understood the other. Great. Okay, this is now an L by N matrix with entries in K. And so this is the way we can describe matrix products by the standard inner product. Now, this will turn out to be tremendously useful, and so I will give this equation here a name. Let's squeeze this here a bit. Whoops. So this is now equation star, and this is what I will need to show the following characterization. I mean, this allows for a more algebraic description of orthogonal matrices. So theorem 1039. So let N in N, and let A be an N by N matrix with real entries. And then the following statements are equivalent. are equivalent. 1, A is orthogonal. 2, the columns of A form an orthonormal basis of Kn. Of course, up to identifying column vectors with elements of Kn. So this is a nice way of describing this, and now it becomes even nicer. We can just check that the transpose of A, which we've seen before when it had dual spaces, times A as a matrix product is the identity matrix. Point 4, A is invertible, and its inverse is given by its transpose. And finally 5, the rows of A, form an orthonormal basis of Kn as well. This looks quite mysterious because actually on first sight you wouldn't expect a transpose to pop up here. So this might look a bit weird. Some of you might even have an idea now why this is the case, but I will now prove this one by one, and this is now a bit tedious because you cannot make a nice application so that by showing this implies this and this and this and this and then go back to the start. But here we really need to prove direct equivalences. So we will show that 1 is equivalent to 2, 2 to 3, 3 to 4, 4 to 5. A bit tedious, but it's interesting really, and a good exercise to really follow this proof and to see why this in fact holds true. So, first of all, let's do the implication 1 implies 2. So I will just list them in this style here. Now, if A is orthogonal, what can be seen in what are the column vectors of a matrix? This is now something I would ask the audience who remembers. The column vectors of the matrix are the columns are the images of the canonical basis vectors under the application of the matrix. This is what we've seen before. So we know that so the columns of A E1 to A E n. So the columns of A are this. Are this, or written in terms of the induced map, Fa of E1 to Fa of En with respect to the canonical basis. Now, and we've seen that, now we're already done because we've seen that any orthogonal map is orthogonal if and only if it maps an orthonormal basis to an orthonormal family. And so this implies that if the matrix is orthogonal, the map Fa is orthogonal, so this must be an orthonormal family in Kn. And since it consists of n vectors, it must be an orthonormal basis. So from this, it follows that theorem 1033, what we've seen that AE1 to AEn is an ONB of K to the n. Okay, this already shows this implication. The proofs of all the implications are not very difficult. It's just a bit tedious to compute them all. Now, the other implication, assuming that the columns form an orthonormal basis, how can we see that it's orthogonal? And this is now kind of the longest computation in this case. So we've seen that these are the columns of our matrix, and now we have to assume that they are an orthonormal basis. So by assumption, AEI inner product with AEJ with respect to the standard inner product. This is again given by this Kronecker delta, delta IJ. So 1 if the indices coincide and 0 in the other cases. This is the definition of an orthonormal basis. So from this we now make a long computation. Namely, for all I and j, this is clear. So we now take two vectors from Kn and we call their entries lambda1 to lambda n. This is a vector v. And W has entries mu1 to mu n in Kn. Then we make the following observation. So we need to show that the inner product of AV and AW is the same as the inner product of V and W. So let's check. Here we can now do this trick because this is now a linear combination in terms of the canonical basis vectors. We know that this is given by A times the sum I from 1 to n, lambda I, ei. This unnecessarily complicated way of writing a tuple in Kn. But here it's really necessary. And then A applied to the sum j from 1 to n mu j ej. So by now using the linearity properties, first of all, A is a linear map, so this becomes the inner product of the sum I from 1 to n, lambda A I times A ei. Here we have the sum j from 1 to n mu j A ej. Now we can use the bilinearity properties of inner products. I'm doing now two steps at once. I'm pulling them both outside. Then, as we've seen before in the previous proof, this is now the sum over all I in n of the sum over all j in n, lambda I mu j A e I A e j. There we have it. So, by this assumption, this is the sum, this is delta ij. So the only ones which are not vanishing here are the ones for which I is equal to j. So in this case, this is 1, which means that this whole sum just becomes the sum from I equals 1 to n of lambda I times mu I times 1. So we don't need to write this down. But just by definition of the inner product, this is the same as the inner product of lambda 1 to lambda n with mu 1 to mu n, which is by definition just the inner product of V and W. So V and W were chosen arbitrarily, so A is orthogonal. Okay, so much for that. Okay, next up, so we've seen that the first two are equivalents, so let's go for the next rounds. 2 implies 3, or basically here we can show the equivalence in one step, because we're only using equivalences here. Now, here's the crucial part where we will need this description here. This is the interesting thing. Now, let C1 to Cn be the columns of A. So let's now do shorthand notation. Columns of A. Then C1, Cn are, if we now consider the transpose here, we know that the columns of the one become the rows of the other. So C1 to Cn are the rows of AT. So yeah, up to identifying row and column vectors. So as you know, I'm quite sloppy with that. Okay. So, by the formula star, we get the following. So this was the formula star. This equation, AT times A equals AIN. So what are the ij entries of this? The entry in index ij of the identity matrix is the Kronecker delta. So this becomes delta ij. So here on this side, by this star, so the rows here are the C1 to Cn, and here the C1 to Cn have the same notation there as well. So in the ij index, we have Ci, Cj. And this holds for every entry. So this is just the equation for one entry written down for all I and j between 1 and n. And just by definition, this is the same as C1 to Cn is an orthonormal basis of Rn, of Rn. So this is a direct equivalence here. This is nothing if we just use this identity, so this observation for matrices, and really write down what we show that this simple equation is very powerful, and that it's actually a lot of equations, and one for every entry. And entry-wise, this is just really a shorthand notation for formulating this orthonormal basis condition. So 2 is equivalent to 3. This is what we've shown. Now, so 3 and 4. So you might actually think, okay, what's there to show? This shows that this is inverse to A. It does not, because this only shows that AOT is left inverse to A. To show that through the inverse matrix, we need to show that this already implies the other equation, namely that A times AT is also the identity. First of all, this one implication is clear, so we're going from 4 to 3. I mean, this is definition of the identity of the inverse here, if it's invertible. So 4 implies 3 obvious, but the complicated thing is the other implication, going from 3 to 4. So if this holds, then if we get an equation for the induced matrix, induced maps, namely the induced map FAT composed with the induced map of FA is the identity on on Rn. So this map FA has a left inverse, and if you think back to the very beginning of Mathematics 1, this implies that FA is injective, and this is now a linear injective map from Rn to Rn, and so an injective map between between vector spaces of the same dimensions is an isomorphism. This was again this famous corollary that we use all the time. 723. FA is an isomorphism, and this of course gives us that A is invertible. Okay, so far so good. So we know that A is invertible, and that from the one side we have to multiply it with AT, it becomes the identity. So we just need to show it from the other side. And it's actually, this you might think, okay, shouldn't this be obvious? But it's not that obvious. Namely, we compute the following. We need to make a nice little computation. Compute, let's see if I can fit this in here. Okay, A times AT is equal to the identity matrix. Okay, sorry, ATA is equal to the identity matrix. This is the assumption. Now, if we multiply both sides by A, this is an equivalence actually because A is invertible. This becomes A, AT, A is A. Okay, this doesn't look really useful, but we can now make a little trick. We can subtract A from both sides. And now we can use the distributivity property of matrices, of the matrix multiplication. That was the one that I forgot in chapter 8 and only gave you shamefully in chapter 9. This was theorem, have I written this down? 913. 913. This gives us that, so A, so, yeah, okay. First of all, here, I mean, what I just said, this is A, AT, A minus A is 0. And now we're using this theorem. This means A, AT minus the identity times A is equal to 0. Okay, but A is invertible. So the only thing that's mapped to, I mean, so one of the two maps has to map a vector to 0 there, if this product here does. But A applied to a vector is 0, since A is invertible, if and only if the vector itself is 0. So since this is invertible, we must get that this here is equal to 0. And sorry for squeezing, this is equivalent to AAT is equal to the identity. And this is what we needed, because now we've shown that, so AAT is the identity and ATA is the identity. So here, let me squeeze this there before erasing. So this implies A minus 1 is the transpose. So indeed, this is the other implication. Okay, it remains to show, so we've now seen that 1, 2, 3, and 4 are equivalent, so we just need to bring 5 into the game. This is not that much work anymore, but let me quickly erase. The final part is actually the simplest one because we can just refer to what we've done before. Namely, first of all, going from 4 to 5, so from this inversion property to the property that the rows of the matrix form an orthonormal basis. This is actually analogously to what we did before. When we've seen, so analogously to this implication 3 implies 2, there we had that AT times A is the identity, which implied that the columns are linearly independent. Now we can just take the other identity, A times IT is the identity, and do the same way with the rows and the columns and so on to show that the rows then have to form in an orthonormal basis using this theorem about matrices and the products that they had before. So this follows in precisely the same way. So analogously to this, using AAT is the identity. And finally, from this row statement, sorry, I just said something wrong. This also goes like before, namely from this column statement, we had this implication. Now the opposite implication to that, we had shown that from the columns being an orthonormal basis, it follows that ATA is IN. And in the same way as in 2 implies 3, one obtains in the same way that AAT is equal to IN, so this is basically this equivalence there, but 4 says more than that. Maybe we need also the other product here. We need to show that it's really invertible. And this now goes in the same way as before as well. So as in the 3 implies 4, so this computation with the matrices that I squeezed in the bottom of the blackboard before. So analogy with this implication with just the rows of A, T, and A reversed, one derives ATA is equal to IN and thereby shows the claim. This gives that it's invertible. So this completes the proof. Okay, so we have plenty of ways to characterize orthogonal matrices. And this is now kind of also, you can just take an orthonormal basis, write them into a matrix as columns, and bam, you've got an orthogonal matrix. Okay, this is now kind of also a machinery to produce examples, so to say. There's one more thing I would discuss, namely the same case for unitary matrices. So we have now characterized the orthogonal matrices. What about the unitary cases? And it turns out there's a theorem which is completely analogously to what we did before, with a very subtle change. And for this, I just need to introduce some notation, and then I will just write down the theorem, but I will not prove it, since it's basically the same steps as before, with a slightly enhanced way of computing things in the following way. So given a complex n by n matrix, if we have A with entries A, I, J, a complex n by n matrix, we put the following, that A upper bar, this should indicate complex conjugation. And complex conjugation is just the complex conjugate of this matrix. It's just the matrix where each entry is the complex conjugate of the entry of the matrix A. So just entry-wise complex conjugation. So here this is complex conjugation. Then in this notation we can now reformulate or formulate a theorem which is analogous to the previous one but for unitary matrices. So theorem 1040, yes. So again, n in n, and A is now a complex n by n matrix. Then the following are equivalent. Let me abbreviate. Are equivalent. Slightly unorthodox notation, but anyway. 1, A is unitary. 2, same as before, the columns of A form an orthonormal basis, but this time not of Rn but of Cn. Okay, and now property 3, there's the one slight difference, namely it's not ATA is the identity, what we had before, but we need to take the conjugate of A and transpose this one. So up to context conjugation here. This is the identity, right? This is the only difference there. Yeah, so the conjugate transpose of the matrix, it's what you call it. So, I mean, the additional conjugation, in case you wonder why this is coming in there, when you think about the definition of the standard inner product on the complex numbers, there is a conjugate involved. So there's a conjugation bar involved in there as well. So it's not too surprising that this pops up here as well. So this is really, if you do the computations there, it really turns out that this then gives back a standard inner product and that the conjugations appear precisely where they should appear. This is just something I will leave to you. Okay, and point 4. A is invertible, and now the same way. A is invertible with inverse matrix is the conjugate transpose. And finally 5, the rows form an orthonormal basis of A form an orthonormal basis of Cn. So basically you prove everything as you did before. You take, you only have to write down this relation between matrix products and inner product in the standard inner product, which now contains some conjugation bars, and then basically you perform the same steps as in the previous proof, and you obtain precisely analogously a proof of this theorem as well. So yeah, let me skip this proof. Okay, instead, I want to go back to, first one more consequence of these results, namely one nice corollary. This has a good, this shows something interesting. Let n be a natural number. If A is an orthogonal n by n matrix, orthogonal, n, more space, sorry. If A is an orthogonal n by n matrix, then we can say something about its determinant. Namely, then the determinant of A is very restricted. It is either -1 or +1. Nothing more than that. And in the same way, we get something for the complex numbers. B, if A is a unitary n by n matrix, then the absolute value of the determinant is 1, which would be the same here. I mean, this is equivalent to saying the determinant is 1, or the absolute value of the determinant is 1, since this is a real number. But here, of course, this could be any number on the circle, the unit circle in the complex numbers. So this is a bit, yeah, more general here. Okay, how to see this? We just need to combine what we've seen before. So, part A. We compute from this theorem 1039 we obtain the following, and now we just make a computation of determinants. 1 is known to be the determinant of the identity matrix. Okay, so far so good. But we've seen now that this is an orthogonal matrix, so by this theorem, this shows that the identity is just A transpose times A. Now, by the theorem about determinants and products, this is theorem, I have to check, 914. This is the same as the determinant of A transpose times the determinant of A. But we've already seen that the determinant of the transpose, this was theorem 917, is just the determinant of the original matrix. So transposition doesn't change the determinant. This is what we've seen. So this is simply the determinant of A squared. And this means the absolute value of the determinant is 1. And this, of course, means since we have a real number here, the determinant is 1 or -1. Okay, part B is now the same thing, just with this one complication of taking the determinant. First of all, this is something that is actually kind of follows from this explicit formula of the determinant that you can see, and from the properties of complex conjugation. One checks from its explicit form. that the determinant of the conjugate of a matrix, so the determinant of A bar, if we just every entry is conjugate, I mean this formula shows that we just have this sum over products of the entries there, and since conjugation is compatible with taking sums and products of complex numbers, this is the same as simply the determinant of A as a complex number conjugate. So this is something I will not prove in detail, but that's easy to see from there. Then we get that 1 is now the determinant of In, which is now by the previous theorem, so theorem 1040. Here we now know that we have that of A conjugate transpose times A. This is again by this theorem, so yeah, doing these two steps at once. So this is from 914 and 917 that we abbreviate. Putting these two together, yeah, using this and the transpose property, there is a slight difference. Namely, then we get that this is the same as the determinant of A transpose times that A. Okay, just by taking that the that of the transpose is just the determinant of the original matrix, and with this product here. But now we use this property, namely this is the same as the complex conjugate of that A times that A. And now we're in business because we've already seen that the complex number times its conjugate is just the absolute value squared. So this is that A to the absolute value squared. And so, of course, this is 1, this is non-negative, so this means that A is 1, which concludes the proof. Okay, so good property of orthogonal matrices. This basically formalizes this property. I mean, we haven't talked that much about this because this is what we will see later. That the determinant is somehow also telling us how much linear map stretches or shrinks some regions. So kind of does it increase volume of elements if we apply a set, or does it shrink? And this basically tells us that it doesn't, because this, so determinant being 1 or minus 1, this basically means that it's volume preserving, so to say. Very roughly, you will learn more about this in the next semester when you discuss multi-dimensional integration theory. That becomes maybe a bit more apparent, but I don't want to elaborate on that so far. Okay, one thing is missing so far in this part of this lecture, namely examples. So I haven't given you any orthogonal matrix. This I want to do now, namely I want to consider the orthogonal 2x2 matrix. And I don't want to give you just one example, but infinitely many, because we will determine all orthogonal 2x2 matrices. So how does this go? It turns out there is a really explicit description of the orthogonal group in dimension 2, namely in the following way. O2, the set of all complex 2x2 orthogonal 2x2 matrices, so real matrices of course, is one of two types. It's either of the matrix which I will call R alpha, which looks the following way. The cosine of alpha, hey, trigonometry is back. Hey, cosine of alpha minus sine alpha, cosine alpha. Alpha in is now somewhere between 0 and 2 pi. And the union of this with one other type, which I will call S alpha. And this looks almost the same. Here we have cosine alpha, sine alpha, and minus cosine alpha down there. And alpha is again between 0 and 2 pi. Wonderful. Okay. Now you might think, what on earth do these matrices tell us? It turns out, if you apply these matrices, I mean, you might know them from physics. This turns out that geometrically, applying this matrix to a vector means rotating the vector counterclockwise. So rotating this, and this alpha is now the angle of rotation around the origin, of course. So we rotate something around the origin, and this is expressed by this matrix. And this here, it turns out, is a reflection matrix. This means we take the reflection of a vector in R2 along some line. This line I will write down later, but this is somehow you can really see this. So it's rotation or reflection. These are the only orthogonal 2x2 matrices. So geometrically, this is really kind of length preserving, angle preserving. Rotations, of course, do this. They don't change the angles or something, and of course not the length. And reflections as well. They don't change the length, and they change the sign of the angle if you kind of want to view this with a sign. But since we're just counting the values of the angles there, so the positive values there, they are preserved. Okay, how to do this? So, first of all, we need the beautiful characterization by our theorem that we had before. So, by theorem 1039. So, there we've seen that the orthogonal matrices of rank 2 must be all 2 by 2 matrices with real entries, such that the transpose times the matrix itself is the identity matrix of rank 2, and this is of course 1, 0, 0, 1. Okay, this is something that we can compute, some product of a 2 by 2 matrix, and we will see that we then get equations for the entries. So if we just give the entries of a 2 by 2 matrix names and just compute this product here and equal to this, we will get 4 separate equations. And these are the equations that we will need, but for these I need to erase first, and then we will compute what's getting out of there. Okay, let's really do the math here. Let's do the computations. For a matrix is a 2 by 2 matrix, which is A, B, C, D, as we just call the entries of the matrix. So the condition A, T, A is the identity matrix of size 2. This becomes the following. So the identity is 1, 0, 0, 1. So the transpose of this is obviously just flipping these two. So we have A, C, B, D times A, B, C, D. So this is what we just need to compute. Now, top left corner, we have the first row and the first column. So A times A plus C times C, A squared plus C squared. Okay, top right, there we have the top row and the right column here, so A times B plus C times D. AB plus CD. Okay, bottom left, we have this row here and the first column, so second row and the two columns in the second row of this matrix. So again, AB plus CD. And here finally we have this times this, so B times B plus D times D, B squared plus D squared. So this matrix should be the same as this, which we can just formulate as a system of equations. So A squared plus C squared is 1. Top down is bottom right is B squared plus D squared equals 1, and here we need to have 0, but it turns out these are the same. So in fact, there's only 3 equations. AB plus CD has to be 0. Okay, now we just need to solve these simple equations. Now, this here, A squared plus C squared equals 1. This describes all points in R2. So like we have seen this x squared plus y squared equal to 1 before. This is the unit circle. And we've seen, I think technically we haven't proven this, but this is fine, that all these points are of the form cosine of something, sine of something. So this is kind of how we get the whole unit circle. Meaning, or basically no, we have shown this follows from the polar coordinate description, but anyway, every point in R2 satisfying this is of the form cosine alpha, sine alpha for some alpha. So applying this to this and to this, we get that, so from these first two here, it follows that there are angles alpha and beta, which are somewhere between 0 and 2 pi, such that A is cosine alpha, C is sine of alpha, B is, sorry for the cut, a little mistake, just for convenience, we just take here B to be the sinus part and D to be the cosine part. This just amounts to changing the angle compared to the other choice, so this doesn't matter. But we can find angles such that this holds true. Now, of course, the description that we claimed contained only alpha. So we have to check how beta and alpha are related, and for this we need to use this third equation, which we haven't used yet. Of course, this must have some implications. So if we now use this third equation, which I label star here, this then gives that 0 is, and now we use our new descriptions here, this is cosine alpha times B is sine beta, plus C is sine alpha, times cosine beta. Now, to anyone who was in my course last semester, I would now ask, and basically to anyone, I would ask, does this look familiar? This is this additional theorem, the theorem about sums of angles for the sine and the cosine. That's a famous property. Namely, this was last semester in theorem 378. This shows that this is the same as the sine of alpha plus beta. So the sine of the sum has to vanish. And we know that the sinus vanishes precisely, the sine of x is 0 if x is a multiple of pi, an integer multiple of pi. So this implies alpha plus beta must be of the form k times pi for some integer k. Okay, and we can restrict this a bit further because, as we know, alpha and beta lie between 0 and 2 pi. So the sum always is bigger than 0 and below 4 pi. So this means as alpha and beta are between 0 and 2 pi, k is 0, 1, 2, or 3. Okay, and here we have to distinguish two cases. So first of all, assume that, so in the first case, if k is an odd number, which means so k is 1 or 3, this means, i.e., beta is one of the following. It's either pi minus alpha or 3 pi minus alpha. Okay, and by the periodicity properties, so we know that this is kind of the same value as this, but plus 2 pi. And we know that the sine and cosine are 2 pi periodic. So this doesn't change anything when we insert, if we insert this or this into sine and cosine, they take the same values. So by periodicity properties, we get that. So the cosine of beta, this is now the cosine of pi minus alpha. And we know that if we shift the cosine by pi, this just changes the sign. So this is the same as minus the cosine of minus alpha. And we've already seen that the cosine of minus an angle is the same as the cosine of plus the angle. So this is minus cosine of alpha. In the same way, we take the sine. The sine of beta is now the sine of pi minus alpha. And here we have the same effect. If we shift by pi, this changes the sign. So we get minus sine of minus alpha. And here's a slight difference. The sine of minus an angle is minus the sine. So if we pull this minus outside, we get a plus. So we get that this is the same as sine alpha. So in this case, we have found our matrix. A is now of the form, so now we just have to trace back. A was cosine alpha. C was sine alpha. Okay, and B, this was this one, sine beta, which is the same as sine alpha. And D finally is cosine beta, which is minus cosine alpha. So this is the matrix I called S alpha before. Okay, in the other case, if k is in 0 or 2, so this means, i.e., beta, so either they two sum up to 0, but as they are no negative, this means either alpha equals beta equals 0, or beta is 2 pi minus alpha. Then we observe in the same way that the cosine of beta, so this is the cosine of 2 pi minus alpha, and as I said, the shifting, so the special case of alpha and beta is 0, this is, follows the same equation, that just treat the second case. Shifting by 2 pi doesn't change anything, so this is cosine of minus alpha, and the cosine of minus alpha is the same as the cosine of alpha. And now for the sine of beta is the sine of 2 pi minus alpha, so we forget about the shift, so this is sine of minus alpha, which is minus the sine of alpha. So in this case, A is precisely given by cosine alpha, and here we get sine alpha, and now the change is now between C and D. Here we get minus the sine of alpha, and here we get the cosine of alpha, and this is the map R alpha. Yeah, so this is the second case here. So this shows that, yeah, every orthogonal matrix is of this form, so O2 is contained in yeah, the set of all R alphas, where alpha is in 0 and between 0 and 2 pi, united with all S alpha, where alpha is between 0 and 2 pi. So technically you just need to show that the other inclusions, so that all R alphas and S alphas are orthogonal, and this is just shown by an explicit computation. You just need to show that they are really orthogonal matrices, and this is just writing down inner products and seeing that it works. So this is shown by a direct computation. Okay. Now, so we completely found O2. These are all matrices that are all orthogonal 2 by 2 matrices. And now let me briefly write down the geometric properties of these maps that I've already mentioned. So, geometric interpretation or geometric meaning. So in the first case, these matrices are R alpha, so the maps induced by R alpha, which would be FR alpha, which is now an endomorphism of R2. This is a counterclockwise rotation around the origin by the angle alpha. This is something you can compute with examples easily, so I will not elaborate on this. I mean, I don't have, unfortunately, I would really like to do this, but I don't have time in this course to do analytic geometry here a bit. Yeah, this curriculum is really strict and full. But anyway, so one further observation, and this is something I will not explain too much, that the only, if you want to compute eigenvalues of this, so you compute the characteristic polynomial and try to solve it, and you will find that this only has eigenvalues if alpha is either 0, then of course we don't rotate anything, and it turns out then you can easily see from R alpha that this matrix is then simply the identity, so nothing happens. Then every vector is an eigenvector, of course, because everything is mapped to itself. Eigenvalue is 1. And it turns out if we insert the parameter pi, this means it's kind of rotating by 180 degrees. This means that some vectors get, all vectors get mapped to minus something. So then we get this effect there. So this is just rotation has then the effect there. But otherwise, if we rotate something by some small angle, nothing except for the origin is mapped to itself. So there are no eigenvalues. Okay, the second part is now the matrices S alpha. Let me do this right there. So F S alpha, again an endomorphism of R2. This is, in fact, and I've unfortunately have no time to really do the computation there. So this is the reflection along a line, and along the following line, the line generated by the vector, so R times, and there we have cosine of alpha over 2 and sine of alpha over 2. So this vector here, this is really the reflection along this vector. How can you prove this? If we here now try to compute the eigenvalues, you can show that this really has two eigenvalues, namely 1 and minus 1. First of all, this implies that Fs alpha is diagonalizable with eigenvalues 1 and minus 1. And it turns out if we really do the computation, I mean the eigenvalue 1 is precisely, this is precisely the eigenspace of 1. This is the line, of course, if you do reflection along a line, the line is just fixed, so nothing happens. And you can really check that this is then the eigenspace of 1 and the orthogonal complement of this. So the vector orthogonal. This is the eigenspace of minus 1. There every vector is mapped to its opposite. So this is something I recommend you to draw some pictures about this, or to draw the idea there and to really do the computation there, because this is quite illuminating. So really try to, you can just, by the standard methods that we had, you can just compute the eigenvalues of this matrix and compute an eigenbasis, or compute the eigenvectors there. Okay, so this is what we had so far. To summarize this, is basically, so we've shown every orthogonal endomorphism, sorry, I can make this quicker, every isometry of R2, so with the standard inner product, is rotation or reflection. So these are the only orthogonal maps. It's beautiful, I think. Anyway, so we know every orthogonal endomorphism is an isometry, so this is the same as before. Now, this is how we can classify the isometries of R2. And there are classification results for higher dimensions as well. So for dimension 3 and higher and so on, there are some partial results about this, but we will not discuss them in this lecture because they take a lot more time to prepare. You can, like in R3, you can also view rotations around a plane. So basically you fix a line, it's like the axis of the globe or something, where you put a line through the north and south pole, you have rotation around this. This would be an orthogonal map, but then you could change the axis and take it arbitrarily and get some kind of the rotation along the plane orthogonal to that axis, and get orthogonal maps and classify orthogonal maps of R3 by this, and also getting a notion of reflection there. Anyway, I will not discuss it about here. So this is the isometries of R2, so this, let's leave it at that. But before we go on, I want to just conclude this section by introducing one additional notion that we will not directly use in this course, at least as far as I see. But you will probably really encounter this definition in a lot of physics situations and so on, and you might also in future math courses. So I will just, for completeness, I want to have one definition on the blackboard. Namely, you do not consider only the orthogonal and the unitary groups. There's more. Definition 1044. So that n and n. The special orthogonal group in dimension n is the following. It's denoted by SON, and this is defined as the set of all orthogonal n by n matrices which have determinant 1. Precisely 1. Before we knew it was 1 or minus 1. It was that's not equivalent, of course, but here we just take the ones which have determinant 1. Okay, same for the complex setting. I have to erase quickly one last time, and then we do that. The corresponding notion for complex matrices, or for unitary matrices, is now defined in the same way. The special unitary group in dimension n is now given by also denoted by SUN, so just put an S in front of it. This is defined as the set of all unitary matrices which have determinant 1. Again, before we only knew that the absolute value was 1, so the determinant could lie anywhere on the unit circle in C. Now it has to be precisely 1. So they are called groups, and this is for a reason, because they are, again, groups if you restrict to this. Namely, if you restrict to the matrix product to matrices of this, by this product rule for the determinants, that determinant of, if you have two matrices of determinant 1, the product of them will also have determinant 1. So this is the way we get another special unitary matrix, or special orthogonal matrix, depending on these cases. But it turns out that they are really, again, groups. So let me just fix that. So 1 SON and SUN are, again, groups with the matrix product. So groups with respect to the matrix product. And these groups become relevant when you consider so-called orientations of vector spaces. This is what you will read probably in Math 3, but also you will encounter this probably in physics, like choices of bases and orientations and directions and so on. For example, when you talk about this three-finger rule for force, so which is the order of something, and there, I don't want to elaborate on that, but this is kind of, those are orientation preserving, if you've already encountered this. So the set of all orthogonal and unitary matrices which preserve orientations, to be very precise. Okay, so far so good. And second remark, we have seen the special linear group before, and there it holds that SON, the special orthogonal group, is the same as the intersection of the orthogonal group with the special linear group. And of course the same for the unitary group. So the special unitary group is the same as UN intersected with SL, the special linear group, SLNC, and this for all n in n. So this was, the special linear group was in corollary definition, there was this mixed form, 916, okay. Now, just as a final example, let us consider another look at dimension 2. So we have seen that what the orthogonal group of in dimension 2 is. Let's take a look at what the special orthogonal group is. So we had these matrices, the rotation matrices and reflection matrices. So let's take a look at their determinants. This is all we need to do. So let R alpha, S alpha be given as above. So in O2 as above. Now, it turns out that the determinant of R alpha, so this was in the main diagonal there, we had the values cosine alpha and cosine alpha. So and we have the standard rule for determinant of 2 by 2 matrices, just this cross of products there. So first the product of the entries on the diagonal, which would be then cosine alpha squared. Now we take minus the product of the other two entries, and we had minus the sine of alpha and then plus the sine of alpha. So this would be minus sine squared alpha. So we would get cosine squared of alpha plus sine square of alpha, which is 1. So these are special orthogonal matrices. And for the reflections, we get that this time we had the minus on the diagonal. We had cosine in the top left corner, in the bottom right it was minus the cosine. So here we would get minus cosine squared alpha, minus, and now this time we had on both other entries were both sine of alpha, so we just get here minus the sine squared of alpha. So this is minus cosine squared plus sine squared, and this means this is minus 1, so they are indeed not special orthogonal. So it turns out the special orthogonal group in dimension 2 is just a group consisting of all rotation matrices. This gives the special orthogonal group. Okay, so much about these matrix groups. This is now fine enough. In the next section, we study another phenomenon for endomorphisms compatible with inner products. Namely the so-called class of self-adjoint endomorphisms. And they are endomorphisms which might look a bit unmotivated at the beginning, but it turns out that many operators and many linear maps occurring in physics actually have this property. And it turns out that these endomorphisms behave nicely with respect to their eigenvalues and the eigenvectors. So yeah, this is what we'll study in the next section, which will then conclude this chapter. See you in the next section.